Okay, welcome everybody. The subject of this presentation is the Java memory model. It's concurrency, but it's way more, I call it, low level than starting threads or using high level blocking or synchronization structures. It really is hardcore Java. My personal interest, I love concurrency. I've been spending time on it for more than, I think, the last 6 years. So low-level concurrency, databases, STM, distributed computing, architecture, scalability, patterns resolving around concurrency control, batch processing, high-volume data processing, so all aspects of concurrency control. Well, you can always call me for it. I really like doing it. It's like the ultimate puzzle. It's way better than Lego. I work on all kinds of open source projects. The first is Hazecast. Does anybody know Hazecast? That's a good number. I'm currently working on a book for the pragmatic programmers. I hope that it's going to be released in a few months. And one of my other projects is called Multiverse. It's a software transactional memory implementation. And in short, if you have a look at the following example, and don't kill me if it contains mistakes, but if you have the following stack class, then you have a very simple node containing an item and a next element, and the stack, of course, has a size and as a head. And if you do the push implementation, is very simple, and the same goes for the pop. The big question is, how are you going to deal with concurrency control? You can easily you could of course add synchronized to both of the methods, and then you're finished. There are other techniques like non-blocking concurrency control. The only problem is that these are very local solutions, and they often don't scale up to a combination of complex data structures. So with STM, you can merge all this concurrency complexity. You can hand off the complexity to the software transactional memory. So in case of STM, the example could be as simple as this. I cheated a little bit because here I use the atomic keyword. In Java you cannot add a new keyword, so you need to use something else. A simple template would be sufficient. In Scala you can make closures. You could make an atomic closure, and then it also is very simple. But the concept is simple. You add your atomic blocks to your methods, and the STM is going to take care of concurrency control. If you take a closer look at the last method, where you see the pop, then if I'm going to pop when there's no element on a stack, I'm going to throw a exception. But in some cases you want to block, and this is something where STM really can be very powerful, because if you want to block, I do the following. I have a simple method here. It's called a retry, and most people would expect you are going to do a busy loop, and you keep on waiting until there's an item on the pop of on the stack so you can pop it. But with STM, you really block on all the references you have read, and you're only going to be notified as soon as you, if one of the things that has been changed is going to be, one of the things you have read is going to be updated. So with STM, concurrency control can be very simple. The only big problem with STM, it's a perfect solution for an imperfect world. Other open source projects I'm working on, gparse, it's a concurrency library for Groovy. Mostly I'm focusing on the STM integration in Groovy itself. Other project I also do for a living is Brooklyn. It's a cloud management system where you can easily scale in and scale out applications in an arbitrary cloud, so as Amazon or Rackspace or any other. And I used to work on Akka. Akka is an Actor STM framework for Scala. And my STM was the initial STM that was used in Akka. Currently it's being replaced by fully Scala-based version. So this is the open source stuff I'm working on. Okay, the agenda. First of all, I want to do a wake-up call. Because most people do not know what the Java memory model is, and they think that concurrency control is simpler than in reality it is. So after the wake-up call, I want to get started with why do we want a memory model at all, and how is it defined, and a very advanced technique, which is very usable. It's called piggybacking. If you have any questions, please ask them. I think I have enough time for it. So I really love to answer questions. So if you have them, just ask them. Okay. Before we begin, concurrency control is complex. So if you can cheat your way out by not sharing state at all, so making things immutable or isolation, that should be the first solution you go for. Only if immutability of isolation is not an option, then you need to deal with complex shared state, and you also need to fall back on synchronization. This is the least preferred solution. So if you can get away with immutability or isolation, please try to do that. First of all, the first wake-up call. It's a very simple structure. It has two methods, foo and bar. The big question is, can it ever happen that the text can't print is going to be printed? Does anybody see why this can or cannot happen? In the code, first I set A and then I set B in the foo method, and in the bar method I first check if B has been set and then A has been set. So according to my program logic, this should not be possible. It should not be possible that I get to C. Can't happen. And following example, it's quite a traditional example. If you make runnables, you need to stop. In this case, we have a field stop. You have a method stop that sets the fields on true. And we have the run method, which does a loop. While not stop, you're going to print hello. The big question is, can you stop this runnable? Is there anybody here that sees an error in this code? Okay. I'm going to come back to these two examples during my whole presentation, so you will exactly know for all kinds of reasons why this code is completely broken. The Java memory model. The Java memory model is not about heap sizes, garbage collection. It's also not about high-level synchronization structures like exclusion, blocking, executors, whatever. It's extremely, extremely low level. In most cases, people, they never get in contact with it because there's no API to program against. But it's certain guarantees that need to be in place by the JVM, and you need to understand those guarantees to correctly make multi-thread code. So the Java memory model defines under which condition a thread is going to see a write made by another thread. So that's the basic. Since the JVM is not dependent on a particular hardware, the Java memory model needs to be hardware and operating system independent. So it should not matter if you use Linux or Windows. It should not matter if you use an Intel or an AMD, or maybe even more advanced architectures like an ARM processor, or not advanced, but more. They consume less power. And the old Java memory model, so that's the memory model before Java 1.5, was very ill-defined. It could lead to all kinds of strange things, like broken finals. So for example, if you have an integer object with a final field, then it could be that you see different values over time for that integer object. Even though you make the field final, it still can happen that the code does unexpected things. So everything before 1.4 or 1.5 is broken. And another important thing is it's missing the safe handoff mechanism, piggybacking. I will get back to that. The new Java memory model has been solved or added to Java 1.5 in JSR 133. So if you ever need to look it up, look for JSR 133 and you'll find the details. Okay, a lot of people think as soon as they deal with concurrency control that their system is going to be sequential consistent. They think that if I write a value to some kind of variable and I read that in a different variable, that the thread is immediately going to see the value that just has been published. The problem is that's not true. So people think that they are going to be protected or the program is going to work in certain ways. Well, in practice it doesn't need to be. And another thing is that instructions, they can be reordered. So it can be that the instructions are being executed in a different order than you wrote them. So the Java memory model is not automatically sequentially consistent. It allows for certain reorderings, and it allows for certain visibility problems. The only reason that this is happening is because of performance. Yeah, the compiler can do a lot of very advanced techniques to make things quicker. The CPU can do all kinds of optimizations to make things quicker. So if you remove all these optimizations, the code is going to be extremely slow. A very simple way to make all your Java programs sequentially consistent is make every variable volatile. Every field of an object, make it volatile, and your application will be sequentially consistent. It's not going to perform, but it will be correct. So the first thing is instructions can be reordered. The CPU can decide to shuffle them around. The compiler can shuffle them around. And modern CPUs, they even have the ability to parallel execute instructions. For example, the Intel CPU, you can, if things are fine, you can do 4 instructions in parallel. So it could be that due to this super scalar execution, this parallel execution, things are going to be executed out of order. So let's get back to the first example. In this example, you see the A and B. A and B do not have a relation together. Yeah, they are independent operations. So what could happen is the compiler or CPU could say, well, I'm going to do this. So now the instructions have been reordered. And because of this, it can now happen that can't happen is going to be printed. If you take a look at the sum task example, here also a reordering can happen. So if you take a look at the while loop, the compiler could optimize it to this. In the previous code you saw that in the while loop, every time you need to check a certain condition. If you can verify that within that while loop that condition is not going to be changed, what's the point of verifying that condition? Just pull it out of the loop, your code will go a lot quicker. So this technique is called a loop invariant code motion, but it's allowed. So this is the reason for this example, that by reordering things can go wrong. Another problem is you have all kinds of memory in your system. You have processor caches, level 1, level 2, level 3. This is, for example, this is what I have at home. I only have a little bit more cores. As you can see, there is a little level 1 cache. Then there's a bigger level 2 cache. Then there is even a bigger level 3 cache. And eventually you have the main memory. So if a variable would be written, it could be that the value gets stuck in one of the caches. You have no control over it. So it could be that you write a value in one of the CPUs, and on a completely different processor, on a different core, you're going to read that value. Yeah, you are going to read an old value perhaps. There's no guarantee that you are going to see a value that has recently been written. Luckily, the AMD and the Intel CPUs have quite a strong cache coherence. What happens is, as soon as you make a write to the level 1 cache, the write is automatically being published to level 2, 3, and to main memory. So it's very likely that it will end up in memory. And also, the caches, they will sniff the memory bus, and they will see, okay, the level 1 cache on core 1 just made a write. I'm going to pull that write into my memory as well. So it's very likely that that change is going to be visible in your CPU, but it's not guaranteed. And this is with the Intels, but for new generations of CPUs, it could be that because of the increased number of CPUs, the amount of cost it takes to keep all those caches in sync is going to increase. So what probably is going to happen is you will have a relaxed consistency for increased scalability. So apart from the level 1 and level 2 caches, there is nothing that can happen. If you have if somebody checked the assembler being generated, it can be that coder is going to make use of registers. And if you have 2 threads and a value for a field is just put in a register and not just published, if a different thread comes in, all the registers will be backed up and they will be replaced by the registers for that specific thread. So if a value gets stuck in a register, it could be that you do not see the value of the different thread anyway. So apart from level 1 and level 2 caches, it can also be that registers cause visibility problems. So if we get back to the example, then in this case it could be that A1 is stuck in the cache, so it is not yet written to the cache of the other CPU. So that could happen. It could also be that the read of A is an old read. So it's something that A has already been written, but it's not visible in this particular cache, so you will not see that value. Now, if you take a look at this runnable, then it can also happen that on the stop method, this write is going to be stuck in a cache. And it can, of course, happen that on the while loop, the read is going to be stuck in a cache. So now we have 2 causes found why the examples can fail. It's instruction reordering and visibility. The Java memory model prevents us thinking about low-level stuff like caches and instruction reordering, because every CPU can be completely different. And you want to prevent that something will work on an Intel, but it's not going to work on a, for example, an ARM processor. So the Java memory model is a very abstract concept, and I think it's a good thing to know what happens on the CPU, but it's also good to know what happens on the memory model. And as long as you obey the memory model, then it's up to the JIT or to the Java runtime environment to make sure that the correct guarantees are put in place. The Java memory model, like I said, it's an abstract concept, and it will be expressed in happen before rules. The first happen before rule is the program order rule. The program order rule is let me see. The program order rule, if you write a normal single-threaded piece of code, then the program order rule is the instructions as if you for your single-thread code. The compiler is allowed to change them as long as the serial semantics of that code is not going to change. Then you also have the monitor log rule. The monitor log rule. The monitor log rule happens to be between the unlock and the lock of the same monitor, and it is not only the intrinsic lock, but also the Java util concurrent lock. So if you fix the example with the monitor log rule, then we could do it simple like this. Yeah, we make stop, we make synchronized, and we make sure that the read is being read in a synchronized block. Apart from the monitor log rule, you also have the volatile variable rule. It's also important to understand that it's only about the read and a write of the same volatile variable. A read and a write of 2 different volatile variables have no happens before relation. So we could solve a previous example like this with the volatile. Now then there are 2 more rules. One is the transitivity rule. The transitivity rule means that if A is bigger than B and B is bigger than C, then A must be bigger than C. So with the transitivity rule, you can combine multiple rules to a bigger system. And then you also have the thread start, join, and interrupt rules. The cool thing about these rules is you can define your own rules on top of lower rules. For example, you have the spring bean rule. The spring bean rule means that a bean that has been created within one thread is going to be correctly visible in another thread when it's going to be used. For akka, I defined the transaction reference rule. It means that a change made in one transaction is going to be visible in another transaction. And I created a few actor rules. If you want to know the details, this is the link to the blog. It's, although it's very detailed, it's very important that this kind of stuff is in place to make sure that your code is well working as expected. One of the cool things about the Java memory model is you can also do piggybacking. But piggybacking allows you to combine the program order rule with all kinds of other rules, and you can do very cool things. I will give you an example what you can do with piggybacking. For example, we have the following code. You have a very simple integer object with a single field value, and we have some kind of class, the integer container. And we have two methods on this container. We're going to update it and we are going to use it. If you want to make this code thread safe, we can do the following. We could make the fields, the reference we could make volatile, and we can also of course make the value volatile. But the cool thing is that the value of the integer doesn't need to be volatile at all. This means that you can hand over objects which are completely not thread safe using a handover mechanism to a different thread. For example, you could use a queue to hand over normal POYOs from one thread to another thread. And that is because of this piggybacking. So to simplify this, we can use this. On a schema, you will have your the write of the value, then you will have your volatile write. The first part is going to be the program order rule. It's not allowed for the instruction to jump the write of a normal value to jump beneath the volatile write. Then you will have the volatile variable rule. And then afterwards you have the program order rule again. So this means that if the write happens before the volatile write, and that will happen always, and if the volatile write happens before the volatile read, and if then you will be guaranteed that the read of a normal variable will contain the write of a normal variable. There's another way you can use piggybacking. The first approach was using the volatile variable, but you can also use the synchronized block. So this is the same example that makes use of synchronized block. So now you safely hand over object from one thread to another. This kind of stuff was not possible in the older versions of Java because it was ill-defined. The only way to do this correctly is to make all fields volatile or all access of fields using a synchronized block or using some kind of other mechanism. Even the finals were not correctly defined. So with Java 1.5, this very basic stuff now works correctly. Now, well, we have the same mechanism here. Because of the unlock this, lock this, there we have a monitor lock rule in place, and the rest is the program order rule on the blue side, and another program order rule on the other side. And now it means that the write of the value in thread 1 will be visible when that value is going to be read in thread 2. So with piggybacking, you can safely hand over data structures from one thread to another thread. For example, you could use queues. And it makes also sharing of things that are going to be constructed, and after they're constructed, they are immutable. For example, a lot of POYOs, like services that get DAOs injected. As long as those POYOs don't change after they are constructed, and they are going to be read only, then the Spring container is going to provide such a piggybacking mechanism for you. So in short, if you want to do multi-threading, then you really need to understand the Java memory model. you really need to watch out for shared state. So as long as you can get away from shared state, please try to stay away from it. It's just, it's very complex. If you get a chance and you need to deal with shared state, at least make it immutable. Or just isolate it. And I think that especially with the increasing number of cores, because currently we have something like 12 cores per CPU, but in the future it's going to be a lot more. It will be a lot more difficult to make CPUs faster because the power consumption is going to increase exponentially compared to the performance gains you get. So I think the current speed, we are not going to get further anymore. So it will be that we get a massive number of CPUs within our system, and because of the relaxed consistency between these CPUs, things are going to go wrong. And if you make sure that your Java programs are written correctly, they will still be run correctly on new generations of software. And also, the other problem is, if you write multi-threaded code, then often it runs fine for some time. Yeah, but it could be that maybe after a week or after a month of running, something strange is going to happen. And it's very difficult to detect exactly where it went wrong, what was the cause. So my experience is, as soon as if you have this kind of stuff, it's almost impossible to get to find the cause of the bug. The only thing you can really do is to inspect the code and make sure it looks healthy. But it's so easy to break something. So you don't want to spend too much time on debugging multi-threaded code, because it really is something that can take a lot of time. And the large number of cores in Intel machines. If you really want to understand more of it, there's quite a good book about it. It's called Java Concurrency in Practice. There's a whole chapter about the Java memory model. It's written by Brian Goods and a lot of other extremely smart guys. For people that really want to understand the theory behind the Java memory model, check the following website. Jeremy Manson was the writer of this thesis, and based on his thesis, the whole Java memory model was defined. So if you really want to understand it, have a look at this webpage. Otherwise, just check out my blog. There are a lot of articles about concurrency, STM, Java memory model, and whatever, or just send me an email and I'm very happy to answer all your questions. So, are there any questions? No questions? Okay, then